ladies and gentlemen. You are welcome to our lecture number 5 on power electronics and drives. I am Kabir Ahmad Bilal. Today we'll be looking at MOSFETs or power MOSFETs. The MOSFET stands for metal oxide semiconductor field effect transistor, and it is a device that is controlled using voltage which is applied through the gate, unlike the BJT, which is controlled using current applied at the base. And the input impedance of the MOSFET is high, and the switching speed of the MOSFET is very high because the switching time is in the order of nanoseconds. And we basically have two types of MOSFETs. We have depletion MOSFET and we have enhancement MOSFET. This is with respect to the types. And as we're supposed to know from 200 level, the MOSFET is three-terminal device. We have gate, where we apply our control voltage. We have our drain, and we have our source. The typical diagram of depletion type MOSFET is given here. This is what we call the N channel. If you look at this diagram, we have the main body, which is the substrate, and it is made of P-type semiconductor material, and we have our source, which is connected to the N region through a metal. We have our drain connected to another N region using metal, and the two N regions are connected with the channel, and the channel is also N-type, and that is why we call this one the N-type depletion type MOSFET. And this is my gate. The gate is connected to the metal and not connected directly to the channel, but we have a layer of silicon dioxide, and that is the reason why it is called metal oxide. The connections, they are metals. We have silicon dioxide, that's where the oxide comes, and it is operating on field effect mode. So that is why it is called metal oxide field effect transistor. And the symbol of this N channel is given here. The thing to take note on is the arrow. When the arrow is pointing in, then it is N channel. And this is called the depletion type because the channel that is connecting the source and the drain is existing physically, while the main body is the substrate, which is made of P-type. So we call this one depletion type because the channel exists. On the other hand, you can have the P-channel depletion type also. You can see my source and the drain, they are connected to the P region, and there is a P-channel that is connecting the two terminals, that is the source and the drain. And the arrow, if you look at it, it is pointing outwards. So because of the existence of this physical P-channel, we call it a depletion type. But I want you to know that the depletion type MOSFET can be operated in two modes. It can be operated in enhancement mode, and it can be operated in depletion mode. Try to differentiate mode and type. With respect to type, we have two. There is depletion type where we have existing channel, and there is enhancement mode. We are going to, type. We are going to see it is the one that don't have existing physical channel. We create it through enhancement process. But the depletion type, they are the ones that can be operated in two modes, either in enhancement mode or in depletion mode. Let us briefly look at how we can operate this N channel in enhancement mode. This is my gate and this is my source. When you connect a voltage between them, we call it VGS. That's the voltage between the gate and the source. And when it is made positive, when you apply a positive voltage here, what happens is this. You find that in this N channel, we have minority holes which are positive. According to law of electricity, these holes will be pushed away by this positive voltage into the main body of the substrate. And in the P-type substrate, we have minority electrons. And these electrons will now be attracted by this positive. So the number of electrons in the N channel will keep on increasing. So that is why we call this one enhancement mode. We are increasing the concentration of the majority charge carriers, which are electrons in the N channel. If you change the polarity, that is, you made this one negative with respect to this, you find that this negative will be attracting the holes here. They will be entering here and will be pushing electron away. So you find that this region, which is supposed to be concentrated with electrons, the electrons will be pushed into the substrate and the holes will be attracted. So this is what we call depletion mode. I hope you understand. The same thing applies to the P channel. If you apply a negative voltage here, that negative voltage will be pushing away electrons, attracting holes, enhancement mode. If you apply a positive voltage here, it will be pushing away holes and attracting electrons, then it will cancel or eliminate this P channel gradually. That is depletion mode of operation. That is with respect to the depletion type, where the channel exists physically. Now, if you come to the enhancement type, the reason why we call it enhancement type, everything is the same with the depletion type. The only difference is that we don't have existing channel, physical channel, connecting our source and the drain. You can see I have my N region for the source and for the drain, but there is no N channel connecting them. So we call this one enhancement type, because we are the ones that will supply the voltage that will enhance the creation of the channel, which does not exist naturally. And the symbol, if you look at it, is similar to the other one, but only that there is breakage here and here because of the absence of this physical channel. So how do we operate it in this enhancement mode in order to create the channel? What you will do is the voltage between the gate and the source, the VGS, you should apply a positive voltage here. That positive voltage, it will be pushing away all the holes into the body of the substrate, and any minority electron will be attracted towards this junction. So as the electrons keep on coming, they will accumulate, and finally you have the channel created of electrons, that is the N channel. So that is what we call this one enhancement type. We are the ones that create the channel by supplying a suitable voltage. What we have here is trying to explain what I have just said. The voltage that creates that channel, it has a minimum value, and that is called the threshold voltage, V subscript T. Whenever the VGS reach that amount, you find that the channel will be created and the MOSFET will start conducting. And this is the P channel type of the enhancement type. You can see I have two P regions for the source and the drain, but I don't have a P channel connecting them. So all I need to do here is to apply a negative voltage between the gate and the source. That negative voltage, because of law of electricity, which says like charges repel, unlike attract, the negative will now be pushing away electrons and attracting holes. As the concentration of the holes keep on increasing here, when you increase the level of this VGS, you will find that the channel will be created. The voltage that is enough to do that is what we call our threshold voltage. And as you can see also for the P channel, the arrow is pointing out and there is no direct connection. Here we have breakages because there is no existence of physical channel connecting the source and the drain. We are the ones that supplies the voltage to create that. And this is the circuit connection when you want to operate it in, if you want to operate the depletion type MOSFET, that is the one that already has the existing of the physical channel. The arrow is pointing in, and this one is what? N type. So if you look at the polarity of this voltage, is positive between the gate and the source, and the polarity of this voltage also is positive between the drain and the source. So we are now operating it in enhancement mode. Whenever this voltage increases, you find that the concentration of the electrons in the channel would increase, thereby enhancing the conductivity of the MOSFETs. And the VGS and the VDS, that is the voltage between the gate and the source, and that between the drain and the source, they are positive, as we can see from this diagram. And ID, that is the drain current which is created, is also positive. But the VGS should be negative for the depletion mode. If you want to operate it in depletion mode, that is to reduce the concentration of electrons in the channel, you use negative VGS. But if you want to use it in enhancement mode, then the VGS should be positive, as I have already explained previously. Now, the MOSFETs can operate in 3 different regions. It has cutoff region, saturation region, we call it pinch-off region, and we have a linear region. Let us look at them from this crisscrossy curve. As you can see, this is where we call the linear region. The reason why we call it linear is because these curves, as you can see, they are somehow straight line. That is, the value of the drain current is increasing linearly in direct proportion with the VDS. But the moment you enter this region, you can see that these curves, they are somehow horizontal, which means the VDS will be increasing, but the value of your drain current will remain somehow constant. Okay? And anything below these curves is what we call the cutoff region, where the voltage is not enough to turn on the MOSFETs. And whenever we want to use a MOSFET for switching, because that's the application of the MOSFET in power electronics, you find that we operate it in the linear region, where there is a direct proportion between the ID and the VDS. And this is what we call the transfer characteristic curve. And it is showing us the relationship between the control voltage, that is the VGS, between the gate and the source, and the output current, which is the ID. And as you can see, as the value of that voltage increases, the value of the current is also increasing until it reaches where it cuts the vertical axis, and that is where we have the saturation drain current, and that is the condition of the pinch-off, where the VGS is equal to 0. Now, the enhancement type, the one that don't have existing physical channel, it is given here, and this is the circuit also that operates it. You can see that these breakages, as I've said, they are showing that it is enhancement. There is no physical channel existing initially. So this is N-type because the arrow is pointing in. So my VGS is made positive in order to create the channel, and my VDS is also made positive. So whenever this one keep on increasing, the concentration of electrons around the channel will be increasing, so that the concentration will reach our threshold value, so that it can create a physical channel that will create the source, that will connect the source and the drain by artificially creating that concentration ourselves using the VGS. And this transfer characteristic curve is showing that when you keep on start increasing the value of the VGS from 0, you see that no ID, no drain current will be created until we reach that minimum value. We call it the threshold value. The moment you reach it, the ID will start increasing exponentially as the VGS keep on increasing. Now, this is the transfer characteristic curve also for the enhancement type. It has also 3 regions. Sorry, not transfer characteristic, but the drain characteristic, where we have linear region. I have explained why it is called linear. We have saturation region, and below the curves is called the cutoff region. I have already talked about this, no need of repeating. So whenever the MOSFET is operating in a circuit, it has 3 parameters which are very important. The first one is called mutual transconductance, which is the ratio of the change in the drain current to the change in the VGS, that is voltage between the gate and the source. Where the VDS is constant, that is where we get the GM, that's the mutual transconductance. We have the output or drain resistance, and it is the ratio of the VDS to ID, that is the output voltage to the output current, and we obtain this one when VGS remains constant. We have the amplification factor, which is the TATS factor of importance, and mu is equal to the output drain resistance times the mutual transconductance, that is my gain. The power MOSFET generally the one that is used in power electronics is the enhancement type. We have seen that we have two types. There is the depletion type and the enhancement type. So the one that is used in power switching is the enhancement type, the one that don't have physical channel, but we created using the VGS, as I have already discussed. And the most areas of its application are in the switched mode power supplies and in high-speed power converters. And the power rating is somehow low. The voltage is maximum of 1000 and the current 50 amp, and the frequency is very high. It can reach tens of kilohertz, which means it can be 10, 20, 30, 40, 50 kilohertz of up to 90. That's the tens of kilohertz. Now, the switching characteristic of the MOSFET, if we want to see what is the relationship between the controlling input voltage and the output voltage, we look at this diagram. We assume this is our input signal, which is V1, that's the high, and here we have 0, which is the low. As you can see, when the input is low, the output also is supposed to be low. But the moment it switched to high, because as I've already told you in our previous lectures, we are using digital signal. Therefore, it should be either high or low. So when it changes to high, our voltage will never rise to high instantly, but rather it will take us some time in order to reach the threshold value where the conduction will start, and that time is what we call our delay time during on-in. And after that, it will take another time to reach the maximum voltage between the VGS, that is between the gate and the source. And after that, it will reach the maximum input voltage, which is V1. So as this remains high, our output also remains high. But the moment you switch it to low, you find that this one at the same time will never abruptly go to 0, but rather it will start decaying gradually until it reaches 0. It will take a time to drop between V1 to VGSP, and that is what we call the delay time during off-in. And from there to fall to 0, we have what we call the fall time, TF. So this is the switching characteristic. So if we go back here, we'll say that what are the determinants, what are the factors that determine the delay during charging, the rise time, the fall time, and what have you. The factors that determine those, they are the capacitances which are connected between the gate and the source, or between the drain and the source, or between source and the drain. Here should be DS, not GS, please. And the switching time also depends on the impedance of the circuit which is used for driving the gate. If the impedance of the circuit is high, definitely the flow of current should be low. Therefore, it will take a longer time, and vice versa. I have already told you that we have a turn-on delay time. That is the time required to reach the threshold voltage. And the value of that depends on the CGS, that's the capacitance between the gates and the source. Then after that, we have another time, that is the time it will take to rise from the threshold value to the VGS, that is the voltage between the gate and the source, and then to reach the maximum input voltage, and that is what we call our rise time, that is TR. Now, during the rising, we have a rise time TR, which depend on the CGS, and that is the voltage, or this is the time it will take for the voltage to increase from the threshold voltage to the VGS. And it is operating, as I told you, we use linear region. But the rise time, during the rise time, you find that your ID, which is the output current, the drain current, will not start rising from 0 to its maximum value. So the total time it will take to fully turn on is the summation of the delay time during charging plus the rise time, which is TR. And whenever you want to switch it off, what you need to do is to discharge that capacitor. That is the capacitor between the gate and the source, CGS. And the total time required to do that is the product of the capacitance times the delay time during offing. And as I have already explained, there is a fall time, which is the time it will take to fall from the BGSP to the threshold value, that is VT. And the summation of these two times should be what we call the offing time. That is the TD off plus TF. Ladies and gentlemen, this is the end of this lecture number 5. Thank you very much for your time. As usual, watch and watch over again till we meet in the next class. Thank you.